4. I have 4 classes in a row, and I lose track of them. Okay, so we've been talking about group homology and cohomology, and we could talk about that for the rest of the term, but we should do something else. So you can find lots more about this either in Weibel's book or just in a book about group cohomology. So what I want to get on to now is what is called homological dimension. So we'll start with the general case for just any ring, and then next time or the time after, we'll start talking more about commutative rings, and in particular, commutative local rings. We'll maybe say a little bit about local rings today. So there'll be applications to commutative algebra, which are important in both number theory and algebraic geometry, and in algebraic topology. Okay, so the first, I want to kind of, well, let's fix notation. So R will be just a ring, as usual, with unity. And we'll work with left R modules, but everything we say also works for right modules. You just replace R with R op. And let me give some lemma. I think we've implicitly used this or said it at some point, but we're going to use these facts today. So if they're not familiar, we can check them in the seminar. So the first is that a module M is projective if and only if x1 out of this module is 0 as a functor. So no matter what other module you put in there, it's 0. Are you supposed to be here? You are supposed to be here. Did the schedule change from the third module? Did the schedule расписание менялся из третьего модуля? Или? Не знаю.
У меня тут с 13:20.
Ага. Я здесь обычно читаю лекции через транслацию. Ага. Ага. А вам нужна трансляция и запись? Ага. Хорошо. Okay. Maybe they changed it and didn't tell me. I don't know. What's that? Okay. Okay. Right. Or if I want to check that a module is injective, N is injective. If and only if. So remember there was a bare criterion for injectivity, that we only had to check the lifting property against ideals. If you translate that into X, it says the following. So it says if and only if X1 from a quotient to the ring by an ideal, if and only if this is 0 for all what? Left ideals J. Okay. And then from this, we're going to use this, but it's also useful for already for us, say, for abelian groups. Okay. So we have what's called the projective dimension lemma. And I'm going to have to give names to everything today because we'll quote things as we go along. Okay, I should have defined this. Okay, so definition. Given a module, M, its projective dimension which I'll write as P dim of Rm. This is the supremum of the links of projective resolutions. Infimum. So if there's a finite projective resolution, we take the shortest one possible, and that's the dimension. So it's actually, minimum length. Of a projective resolution. So this can be infinite, but it might be finite. So we've seen very short projective resolutions before. For instance, Z mod n has a projective resolution of length 1. There's something in degree 0 and something in degree 1. So Z mod n as an abelian group has projective dimension 1. And we have the following projective dimension lemma. This is about looking at the supremum of projected dimensions over all modules for the ring. So the following are equivalent for a fixed ring R. So one is that the projective dimension for an R module M. So this is going to be a lemma about the projective dimension of a fixed module M. So I could ask for it to be bounded by D. I could put a condition on the x's. I could ask for x'd I from M into N to be 0 for all I bigger than D and for all other modules N. Or I could just ask that for the next step at D plus 1. And finally, I could ask that in any projective resolution, any projective resolution of M let's write it out. So any projective resolution P dot to M, I want the kernel of this differential to be projective. In particular, I can take the given projective resolution, I can go out to this stage and then take the kernel, that will be projective, and then throw away everything else. Make it zeros, and that will give a projective resolution of length D. But what's interesting about this is that it works for any projective resolution, not just a fixed one. Okay. So let's give the proof. And there'll be something similar for injective dimension. Okay, so note, we can compute X using projective resolution in the source. So 4, if this is true, then in particular, there's some projective resolution of length d. Okay? Therefore, the projective dimension is bounded by d. But also here, if I use this projective resolution to compute X, it will vanish above d, in particular at d plus 1. So 4 implies 1, implies 2, implies 3. Okay, so that's all obvious. What's interesting is 3 implies 4. So let's check that. So let's take some projective resolution. So fix a projective resolution. M, P0, P1. Let's look at the segment about which we know something. Keeps going. And let me give the kernel here a name. I'll call it KD for kernel. So this is the kernel of this differential. And I want to see that it's projective. Okay? Well, I know how to check by the lemma. I know how to check whether it's projective in terms of X. Okay? So to see KD projective, let's compute X. Okay, into some n. Okay, so let's compute X into some n. Right. So if I continue from KD, I get PD, PD plus 1, and so on. So I get a projective resolution of KD. So, but PD plus dot to KD is a projective resolution. So I can use it to compute X of KD. So X1 of KD into some n, it will be kernel mod image for Hamming this complex into n. But this complex is the far part of the projective resolution of M. And so this will be X d plus 1 into n. Okay. And this is 0 by hypothesis. Okay. So KD is projective, because all the X1s out of it vanish. Okay, so that's what we needed to check. Very good. And now there's going to be something similar for injective dimension, and then we're going to relate the two. So definition. The injective dimension of a module n is the minimal length of an injective resolution. So I'll write it as IDIM. This is the minimal length. And it can be infinite. Maybe there's no finite length. We saw that this was 1 for abelian groups, right? For any abelian group, there was a natural injective group into which it injected. Namely, it was a product over Q mod Zs. And then whatever the co-kernel of that is some divisible group, therefore injective. So that's the 2-step, well, 0 and 1-step injective resolution. So unless the module is already injective, it has injective dimension 1 for an abelian group. So now we have the injective dimension lemma. Which says the following are equivalent for a module n. So one is that the injective dimension is bounded by some d. 2, x into n maybe I'll just write it as a functor. So this is 0 for I bigger than d. 3, same but for just in degree d plus 1. And 4, in any injective resolution. Hold on. Yes, this is correct, and there's a typo in Bible. He switched the source and target. And for any injective resolution, let me write it as n maps to I upper dot. The co-kernel is injective. So this is really a lot like what we just proved. And in fact, the proof is so similar, I think I'm going to just leave it as an exercise. The only thing I would suggest is to use this characterization of injective, but otherwise the proof is exactly the same. So the proof is an exercise. Just kind of read the proof for the projective case backwards and change kernel to co-kernel and so on. Proof is an exercise. Now we want to put these two notions together. So for a given module, the projective dimension and injective dimension may have nothing to do with each other. For instance, for an abelian group, Q mod Z is injective, but it's not projective. So injective dimension is 0, but projective dimension is 1, I think. We should check. However, if we go over all modules at once, we get something more general. We get a relation between them. So this is called the global dimension theorem or homological dimension theorem. It's a theorem so some people call this global dimension, some people call it homological dimension. So it says the following. So the following so one is I could take the supremum of the injective dimensions. That may be infinite, of course. Or I could take the supremum of projective dimensions. Or I could just take the supremum of the injective dimensions of R mod J's. So it might be hard, to think about the supremum over the injective dimension of all modules, because we don't know anything about all modules. But for some rings, you might be able to understand this. And for the supremum over I such that there's a non-zero x in that degree. So this is for some m and n. And so definition, whatever this value is, possibly infinite, it's called homological dimension of R. The value in the theorem, the common value, is called homological dimension, or sometimes global dimension. And if you're being very fussy, we're working with left modules. And so this would be left homological dimension. A priori, that might be different from right homological dimension. Under some hypotheses, you can show they're the same. We're mostly going to apply this to two commutative rings anyways, in which every left module can be made into a right module in an obvious way. Okay, so let's look at the proof. Okay, so some of the equalities are obvious. Yeah, so this is the supremum over n a module, m a module. Here, J, an ideal, a left ideal. And here, this is over I, a natural number. It could be infinite, right? There might be some module which has infinite projective or injective dimension. So in fact, we've seen that. When we were working with the group algebra of Z mod 2, we computed, it's the common value in the theorem. So the theorem says all of these are equal. And then by definition, that common value from any of these four things, they're all equal, is the homological dimension, possibly infinite. No, for some m and n. So you kind of look over all m and n. And so if this number is finite, it's in particular telling you you'll never see an x in degree beyond the dimension, no matter which pair of modules you take. Now, it can definitely be infinite. So for instance, well, let's just do two examples. So the homological dimension of integers is 1, because we always have this injective resolution that goes 0, 1. Okay? And from that, we can compute x and see that x1 is the biggest that ever appears. If I have an abelian group, I always have this is my I0, this is my I1, where it was over all homomorphisms from A to QZ. Okay. So that's one example. Let me give an infinite example. Well, here, let me give another example. Let's say K is a field. Let's say R is a field. If R is a field, then every module is free. There exists a basis. Every module, well, a module is just a vector space. And by a Zorn's lemma type argument, you can show that there exists a basis. As a basis, so every module is free, and free in particular is projective. So everything has a projective resolution of length 0. Okay, so those are the two easiest examples. We'll see, let me give an infinite dimensional example, and then we'll see other intermediate examples, but that will take more work. So all finite values are also possible in practice. So let's see. Suppose R is the group algebra, say over the integers, of the cyclic group of order 2. So then we know we computed this. The group cohomology is an X. This is Xi over the group algebra from the trivial module to itself. This is non-zero for infinitely many I. I forget which one's which, homology or cohomology. So this is either non-zero in even degrees or odd degrees. Okay, this is non-zero for infinitely many I. And so this number here is infinite, so the homological dimension of the group algebra is infinite. However, if you do group algebras, sometimes group algebras, depending on the coefficients, have finite homological dimension, or even homological dimension 0. So we saw this, a bit of this last time. When we had a finite group, we looked at a ring of coefficients in which the order of the group was invertible. So G is finite, and the order of G is non-zero in some field, then it's invertible. Then you can check that the group algebra here has homological dimension 0. This is a consequence of what's called Smashkey's theorem. So we'll do an exercise about this. So here's a bunch of examples in low dimension. There's more you can say about low dimensions. If you look in Weibel's book, there's a whole section about that. So he considers everything that can possibly happen in dimension 0 and 1. From dimension 2 on up, things get much more complicated, as always in mathematics. Okay. So sometimes dimension 2 things are manageable and dimension 3 is hopeless. So let's do the proof. We didn't prove it, we just gave examples. Right. Let's see. So the lemma, which I rubbed off, the projective dimension lemma for a fixed module, and the injective dimension lemma for a fixed module, told me that I could measure whether or not something was injective by measuring x1s against these things. And then I could measure the injective dimension in terms of the length of an injective resolution, or equivalently in terms of the vanishing of some x beyond some degree. And similarly for projective. Okay. So 1, 2, and 3 no. 1, 2, and 4. 3 is a little different. Okay. So proof. So by the projective dimension and injective dimension lemmas,
Somebody just messaged me that the camera is not capturing this photo.
not capturing this one.
Yes.
That's bad. Can we move it? It's usually getting this one, not that one. Maybe they moved it because this is broken. Well, that's reasonable. Sorry about that. I'm not going to give the beginning of the lecture over again. So we'll just proceed from over there. Well, you win some, you lose some. Does that work? Yeah. What? This one is visible.
Yeah, but I mean, maybe we could call someone who can change the direction.
I think it's probably done deliberately because that board is broken. That's my guess. And one of the secretaries said something about something being broken and they fixed it. So maybe that's what it was. Okay. Well. My wife once accused me of not noticing things. We were out walking, and we were very young. It was before we married, and I said, "You think I don't notice things?" I looked at her, and I was very upset, and I ran into a tree, just as I said this. Okay. Okay, so anyway, is this visible? This is visible. Okay, so by projective and injective dimension lemmas, these two, 1, 2, and 4, are the same. We know how to measure injective dimension of a fixed modules in terms of the range in which x are non-zero. And 2, let's see. Looks like fine. Sorry, I meant projective dimension here. Because we're humming out of R mod J, so we care about it, how long a projective resolution of R mod J is. Okay. So also, note that 2 is greater than or equal to 3, because the supremum here is over a bigger set of modules. It includes this set. So we're interested in the reverse inequality. So we want this. And so for this, we can control R mod J's. We can measure the projective dimension of an R mod J in terms of an X, and we know how that behaves with respect to injective resolutions. Okay. So if we want this, if 3 is infinite, if 3 is infinite, 2 is automatically infinite, and then this is okay. So assume that 3 is finite. And choose, and suppose, so let's call it equal to D. And suppose N is a module with injective dimension bigger than D. Okay, so choose a resolution of N, choose an injective resolution. N injects into I0, goes to I1, and so on. Continues like this. But it has an image here, I'll call it CD. And I want to see that this is in injective, so that actually the dimension of this is bounded. And then the x will be bounded. Then the x will be bounded, and then the projective dimension of this, of 2, will be bounded. Okay, so let's see. So then, for all ideals, J, we have what? We have x1 R from R mod J into N. This will be the same as xd plus 1, not into N, but into CD. This will be the same as x d plus 1 into R mod J, from R mod J into N. Okay. And this we know is 0, because we've assumed that the projective dimension here is D. So we know x1s beyond this are 0. Therefore, since x1 out of R mod J for every J into CD is 0, this implies that CD is injective. Okay. So actually, I didn't even need to assume this. I just assumed that N was some module, and I choose an injective resolution of it, and then I look at this co-kernel. Hence, the whatever N was, its injective dimension is bounded by D. And this is our okay, sorry. That's fine, that's fine. Where is it? Okay. So I already know that this was assumed to be D, which was equal to this. So actually, maybe I should have assumed this. So suppose N is a module of injective dimension greater than D. Then this would be a contradiction. Yes. Okay, so what are we trying to do? We know that 1, 2, and 4 are all equal from...
I got everything up until we rolled the projective resolution and rolled the...
let me repeat. So everything is 1, 2, and 4 are equal. And we know that this one is no bigger than this one, because this is a supremum over bigger modules. So we would like to know that this is no bigger than this. But whatever this is, it's equal to this. Okay. So we're actually going to be using this number and comparing it to this number. We show 1 is no bigger than 3. So pick some module n. Consider an injective resolution of it. I want to claim that actually it eventually terminates at degree at most d. Okay. So I don't think it should be formulated. Weibel says it as a contradiction, but that's kind of overkill. So let's just take a module. Let's choose an injective resolution. Look at this co-kernel term. Okay. Compute x out of R mod j for all j. By assumption on R mod j, this vanishes beyond this degree. Okay, I assume that it's finite and equal to d. So this vanishes beyond degree d plus 1. And then, therefore, this x1 vanishes. Therefore, CD is injective. So there's a bound on the injective dimension. But this injective dimension is what appears in 1, which is equal to 2, so it's no bigger than 3. Okay, very good. So we have this. And now the next task, I should continue over there or here. So we have about half an hour, right? Okay. So the next task is to see how this homological dimension changes when you pass from one ring to another. So there can be a bunch of theorems about this in special cases. So we're going to have what are called change of ring theorems. For this homological dimension. So we'll consider a map between two rings. And we'll either take an S module and restrict it to an R module, or take an R module and induce it to an S module. And we'll see how the homological, the projective dimension module changes. So the first theorem is called general change of rings. So this is just something that always works without any hypotheses on R and S. And it says that let M be an S module, then I can restrict it. I won't write any notation for restricting. I'll just let it be understood. So I can consider M as an R module and ask what its projective dimension is. And the claim is that it's no bigger than the original projective dimension over S plus I can consider S as an R module and ask what its projective dimension is. This is projective dimension of S as an R module. So that's the theorem. And in fact, it can be much less. So for instance, if R was a field, we know a field has homological dimension 0. So if I have a S module and I restrict it to a field, it automatically becomes projective dimension 0, even if this is very big. So it can be very far from an equality in general. So proof, it's going to use this horseshoe lemma about how to piece together projective resolutions. So if either of these two is infinite, then of course it's bigger than whatever's on the left-hand side. Okay? So we may assume the right-hand side is finite. So M is finite projective dimension over S and S over R. So let's give them names. Let's suppose the projective dimension of M over S is N, and the projective dimension of S over R is D. Okay? And so what we'll do is let's choose a projective resolution of M over S of length N. So choose an S projective resolution. P0, P1, up to Pn. That's over S. Okay. And now I can restrict each of these to be an R module, and I can resolve them as R modules. However, I want to consider, how am I going to do this? I want to consider the images here. So take the kernel of each of the differentials, and then it's surjected onto like this. Okay, so this one is actually an isomorphism, so I think I should number them this way. Okay, so these happen to have names. They're called the syzygy modules for this resolution, but they are what they are. And now, step by step, let's construct a projective resolution of M as an R module. We'll use horseshoe lemma. To construct how will I do this? So let's construct R projective resolutions, so projective over R, which look like the following. So I'll have P0, and I'll get a projective resolution there of length at most D. I can do that because this is projective. It's the it embeds into a free S module, and S has projective dimension D over R. So I'll start there, and then the next step will be I have K1 surjected onto by P1, and then the kernel K2. And now I can resolve this. Maybe maybe I'll call this prime. This also has length at most A. Like that, and then by the horseshoe lemma, I can arrange for this to be kind of a direct sum of the two things with a twisted differential. So I'll write a plus with a kind of tilde on it to say that, well, it's not quite the direct sum of complexes because there's a off-diagonal term. Okay. So I can continue like this. So continuing like this, so I'm just going to call this one. This is what I call Q1 dot. So continuing like this, I get projective resolutions of Pi of at length at most D and such that the composite of two of them in a row, if I go from this one to this one to the next one, the composite's 0 because Q3 will surject onto this one, which will inject into this one, which will die in the quotient here. So going from Q3 to Q2 to Q1 will compose to 0. So that's where we use this horseshoe lemma. And then altogether, what do we get? We get a double complex what's it look like? So I'll have here, I'll have Q0, 0, Q0, 1, 0, up to QD, 0. Here I'll have Q1, 0, Q1, 1, and so on, up to QD1. So each of these columns is the resolution of P0, P1, P2, and so on. The last one is resolution of Pn. This is Qn0 up to Qnd. Okay, so I get a double complex like this. And if I augment them with my p's, it becomes exact, like this. And so now, the acyclic assembly lemma says if I take tote sum of this, because I have these exact rows, it will be exact. This would be M out here, the thing I'm trying to resolve. So by the acyclic assembly lemma, which is what we use when we balance Tor and Ext, tote plus of this double complex Q dot dot is a projective resolution of M over R of length of length what? So there's d here and n here. So d plus n, if you count the number of diagonals. Okay, so that gives the bound. We constructed a resolution of length d plus n, and therefore we get this inequality. Okay, so that's the proof. It's kind of tautological, or not difficult, because there's no hypotheses on R and S. Now we would like to go the other way. I see. Well, there'll be, no, not yet the other way, but we're going to consider a special important case. So now we have what's called the first change of rings theorem. And the next two theorems, this first change of rings theorem and the second one, they are what allow inductive arguments for projective dimension. So suppose x in R is central. So I'm allowing R to be non-commutative. If it's commutative, central's automatic. So suppose x is central. The reason I want it to be central is I want to form the ideal generated by it. And if it's central, this ideal will be left and right. Okay, so suppose this is central and a non-zero divisor. So multiplying with it, the only thing that is annihilated is 0 itself. And let M be an R mod X module of finite projective dimension. Then I can ask, what is its projective dimension as an R module if I restrict from R mod X to R? And the answer is it just increases by one step. Now, one step has to do with this extra variable, or this extra element X. So this is projective dimension of the module over the original ring plus 1. So restricting along a quotient by one of these central non-zero divisors only increases the projective dimension by 1. Okay. Much time. So first thing to note is that the original M cannot be projective as an R module. So note that X times M is 0. So M is not projective over R. One way to say it is that, well, there's a bit of Tor 1 because of this. But if it were projective, it would be a summon of a free module and would have no Tor. Maybe there are other ways to phrase it in terms of X. So So whatever appears on the left-hand side is at least 1. So projective dimension over R is greater than or equal to 1. So let's consider the case where it started out being 1 over R mod x. So if the projective dimension, this is an inequality, yes? Or it's an equality. This is an equality. Okay, good. So suppose if M is projective over R mod x, okay, then it's a summand of a free module of a free R mod x module. Which has is of projective dimension 1 as an R module. Because of this resolution. So R mod x, the free module of rank 1, is resolved over R by this, and this is actually a resolution because x is a non-zero divisor. Okay? So in this case, when M is projective, we have projective dimension of M over R equals 1, which is the projective dimension over R mod x, because that was 0 if M was projective. And this is the projective dimension of R mod x over R. Okay? So it works in that case. Now let's suppose let's consider the next case. So we're going to do this by induction. So next, let's suppose that the projective dimension of the module that we're trying to study is greater than or equal to 1. We just did the case that it was equal to 0. So choose a presentation M P0 K 1 0 over R mod x with P0 projective. So the beginning of a projective resolution, we'd have to continue it. Then, how do these projective dimensions compare? Then the projective dimension over R mod x of M is the projective dimension of this plus 1, because the projective resolution of this is one step shorter than for the whole thing of M. So this is projective dimension of K1 plus 1. And then by induction, on the projective dimension, so we already treated the case of a module which had projective dimension 0 over R mod x. So by induction on projective dimension, we have the following. So there's our equality that we're trying to establish. So I can apply this equality now by induction to the module k plus 1. So the right-hand side equals what? It equals projective dimension of k plus 1 over R. And this, by hypothesis, we started out being greater than or equal to 1. So whatever projected dimension of K1 is, it's at least 1. And now the claim is there are two possibilities. Okay, so I want to control this. So either the quantity we're trying to understand on the left-hand side of this equality, projective dimension over R, either it's already equal to this, or, and we're done, or how could it fail? Or, and we'll have to explain this, I claim that the projective dimension of this projective module I know that has to be 1 because this has it's projective, therefore a summand of a free, and this has projective dimension 1. I claim that this must be the supremum of the projective dimensions of M of K1 and the projective dimension that I'm trying to understand. So that follows from considering this short exact sequence. So the latter claim follows from what? So I could hum in some module n. Into this, I would get long exact sequences of x. So applying long exact sequence of x i's into n. So let's call this star. So this has projective dimension 1 over R. So if I get the long exact sequence, the most I'll get here is an x1. And beyond that, everything will be 0. So x2 out of this will be x3 out of this, and so on. And I know that this is equal to 1. Just a minute. Right. So I'll see the X1. If both of these were 0, I would be getting no X1. So I need to be shoot. Just a minute. So it looks like I'm assuming this is not the case. And I know from the general change of rings theorem that I at least have an inequality. Right? I always know this is less than or equal. So the only way this could fail is if it were a strict inequality. So if this is a strict inequality, shoot. So Weibel doesn't explain this, and I figured this out this morning exactly in this way, but now I forget. I will remember in the seminar. Let's check this in the seminar. It's not hard, but I'm forgetting this step that we need. So I figured this out this morning in 1 minute. Okay. So let's assume this for the moment. What do we note next? Okay. So we know that this should equal 1. We want to eliminate the possibility. What could go wrong? What could go wrong is that this was strict because this was equal to 1. Okay. So we need to eliminate the following possibility. That the projective dimension of this over this did not change, was equal to 1 and did not change. So the argument is as follows. I think actually the thing I may be confused about is the direction of the original inequality. Just a minute. No, that's correct. Okay. So how do we do this? So let's choose. Free is not so important, but let's choose a free module. It could be projective. F that surjects onto M and has some kernel K. If the projective dimension, so I guess this is over R, if the projective dimension here was equal to 1, then this would be projective by the projective dimension lemma. And now if I tensor with R mod x, what do we get? So here I'll get M itself, because M was already defined over R mod x. I'll get F mod xf. I'll get K mod xk, whatever that is, and then there'll be a Tor1 term. And the next Tor1 term will be 0 because f is free. But how do we compute Tor1 against R mod x? Using this standard resolution here of R mod x, we see that the Tor1 is just the stuff annihilated by little x. But that's everything. This Tor1 term for any module, it would always be m such that xm equals 0. Okay. But because x acts trivially on m, in our case, that's just equal to m. On the other hand, if the projective dimension of m over R mod x was less than or equal to 2, then this would be projective over R mod x, this would be projective over R mod x, so this would have to be projective. Would be projective over R mod x. Just because they're in any beginning of a projective resolution, the kernel in that degree would be projective. However, it's 0. However, it's equal to m. It's equal to m, which we were assuming is not projective. And so this is a contradiction to the hypothesis here. Okay, so it's a contradiction. This is not possible. Okay, so that's the end of this proof. We'll have one thing to check in the seminar. There's probably a better way to organize it, so we can come up with a better organization of the proof in the seminar. So this is the claim that Weibel makes. It can be checked by studying this long exact sequence, but there's probably an even better way to organize it. So let's stop there for today.